Thanks, Anne. Yeah, I'm very excited to be here giving this talk. It's on joint work with Lowen, Nick, and Henry. And the first thing I'm going to do is just give you the one-sentence summary of the entire paper and talk. So here it is. In a single sentence, the computational security of a three-message quantum interactive protocol can be amplified by parallel repetition. And the next thing I should do is give you the definitions of all these words. And the way that I'm going to define things is through a motivating example. So the example I've chosen is the quantum bit commitment. It's a cryptographic equivalent of a message in a locked box. So here you have like a little box, and someone can put a message inside of it, and then later they can take the key and open the message for someone who they want to show the message to. The reason I've chosen quantum bit commitments is because they're very important in a lot of places in quantum computation. So they're implied by almost every other cryptographic primitive I can think of. They have connections to complexity theory via like unitary synthesis and the Ullmann transformation problem, which we saw on Tuesday. And there's also a lot of conjectures in physics that kind of imply these objects would exist. So they're just overall important, and I think it's a good example. So let me give you in more detail what a quantum bit commitment is. There are two phases in a quantum bit commitment. So first is a commitment, and then there's a reveal. So the setup kind of starts like this. To commit to a bit B, so here you see like psi B, the sender will create some bipartite state psi B. And I'll point out this state will be efficiently preparable, and that'll come in later. But for now, just think of it as some state that the sender has, and there's two of them, one for 0, one for 1. And he's going to send the commit register, noted by C, to the receiver. So after he does that, he'll hold on to the R register, which will kind of be the key that he'll send later. And the receiver will have this commitment to some bit B. And they'll go about their day and they'll do other things. And at some time later, they'll come back together, and the sender will want to reveal the bit that they committed to. So here, the setup is the same as it was before. The sender holds the reveal register, and the receiver has this commitment. And then the sender sends this reveal register along with the bit B. So after they do this, the receiver now has the whole state, and they can just check that the sender actually did give them a copy of the state psi B, and now they know what the sender put in the box initially. So this is an example of a interactive protocol, which is the first word that was used in that one-sentence summary. But these protocols don't really have much meaning unless we can say something about them. So what would we want out of a quantum bit commitment? One property that we want, which we can kind of call like the security of a commitment, is that after you put the message in the box, the sender should not be able to change that message until they unlock the key, right? So here in this setup, imagine this is after the sender has sent the commitment register to the receiver, so they hold the reveal and the receiver holds the commitment. This is what we don't want to be able to happen. So for some reason, they've sent the reveal register, but they've also sent the other bit, 1 minus B, and the receiver has successfully attained a copy of the opposite commitment, and so the receiver is totally convinced that the sender actually put 1 minus B into the box initially. This is not a good thing. For example, like if you're in an auction and you've put your bid in, you don't want to be able to change that bid. Or if you're like voting, you don't want someone else to be able to change your vote. So you just don't want you don't want to allow these commitments to change once they've been put into the box. And this is a nice property, but how do we actually formalize this property? How do we characterize whether or not a scheme has this? For this, we're going to introduce these computationally sound protocols, which in cryptography we call them a security game. So this is like a little game. It's like a thought experiment. So it's not a real game, but it's a game that you could imagine happening that would kind of certify that your particular protocol is sound. So let me explain the game for this security property, which is actually called binding. It's a little different than how how the commitment actually goes down. So in the binding game, an adversary is trying to convince a challenger that their proposed scheme is not secure. So what the challenger does is he says, okay, well, how about I make a commitment to 0? So this is size 0 with the reveal and commit registers. And I'll send you, the adversary, the reveal register. This way I know that the commitment has kind of been honestly created. If I let the adversary just send me a commitment, then they might do something I didn't expect. So the challenger will generate the commitment to 0. They'll send the reveal register to the adversary, and the adversary can do whatever they want. They can apply a unitary, they can measure it, they can, do whatever they want to do to try to change what the message was. And at the end, they'll send back the reveal register. And the adversary will have won the game, won the security game, if they can successfully switch their commitment psi 0 to psi 1 at the end of this process. So this is just a protocol, and when we say it's computationally secure, we mean that no polynomial time adversary should be able to win this game with some high probability. And the notation I'll use is that the game or the commitment scheme is epsilon binding if no adversary who's efficient, no efficient adversary, can win this binding game, security game, with probability greater than epsilon. Okay? Now I'll take a brief aside from quantum bit commitments just to show you the outside world. In general, this would be called soundness. So if you gave me a protocol, here an adversary and challenger do some interactions, and at the end, the challenger decides whether or not the adversary has won, the soundness of that challenger would be called the maximum probability that any adversary, efficient adversary, can win this protocol and get accepted would be called the soundness of the challenger. But let's go back to quantum bit commitment. So, the number epsilon is really a characterization of how good our commitment is. So let's say someone gave you a really bad commitment. So here, someone has walked up to you and said, I know a commitment scheme that's 0.99 binding. Now, I'll remind you what that means. It means that someone could commit to you, and 99% of the time they could successfully lie to you, but 1% of the time you would catch them in the act. So it's not very useful, right? Basically all the time they're able to change their commitment. They can make it whatever they want without actually opening the box for you. But then you would, a natural thing to ask is, this is not a very good commitment. Can I just do it twice? Can I just, force you to send me 2 boxes with the same message? And, in order to switch your commitment, you would have to switch both of them. Intuitively, ideally we would show that this is 0.99 squared binding. And, this generalizes to k mini copies, 0.99 to the k. Intuitively, you kind of think what could happen other than, the adversary will try to flip the first one, and then they'll try to flip the second one. But, they can only flip the first one with probably 99% probability, and they'll flip the second one with another 99% probability. So, clearly they can't flip both of them with better than 99 squared % probability. And despite being so simple in our heads, it's very difficult to actually prove that this works. And it's been an open question for some time. So the goal of our paper is to prove that this is exactly the behavior of these protocols under what's called parallel repetition. The reason why it's parallel is because we're sending both of the commitments at the same time. And before I move on, I will again show you the outside world. I'll pull the covers off of your head. And this idea of parallel repetition appears in a lot of places, not just for quantum bit commitments, but also in all these places. I'm just flashing them on the screen, but for the purposes of this talk, we'll stick with quantum bit commitments. But it is good to know that this is a generally useful paradigm, and we're not just focusing on this one, or we're not just proving something about this one narrow use case. So next I'm going to tell you what the actual result of the paper is, maybe in more detail than the first slide. So here it is in a little bit more formalism. So for every 3-message computationally secure quantum interactive protocol with soundness S, the k-fold parallel repetition has soundness S to the k plus some negligible term. So there it is, and this is a bit abstract. So, oh shoot. I did not intend to do that. One sec. Okay, cool. Like I said before, this idea of parallel repetition appears in a lot of places. So as you expect, we can just check off all these boxes and these things all work, but we're going to focus on quantum bit commitments for the purposes of this talk. I think that'll be easier to understand for everyone. So here we are again. Someone's handed you this commitment scheme, psi0, psi1. It's just a pair of efficiently preparable states. And you know that the maximum probability over all polynomial time adversaries that the adversary can win this security game is at most 0.99. And you would ideally get that 0.99 down to something very small, ideally like negligible in some security parameter that you know of. And concretely, what our theorem says is that if you instead play this game, instead of with one copy of psi0, you just take some large polynomial number of copies of psi0 and you send them across, and then the adversary is trying to flip all of them to psi1. So in this case, remember, like if even one of the copies is not psi1, it's still psi0, then the adversary loses. So what our theorem says is that the probability that any adversary can successfully flip all polynomial many copies of this is some negligible term in the security parameter, which I'm not focusing on now, but at a high level, that's basically what the theorem says. And this means that you can build so-called standard quantum bit commitments from a lot of things. There's lots of times where you make an assumption that leads to a weak quantum bit commitment, like for example with black holes, like you don't get a strong commitment out of the box, you get something weaker, and you'd like to amplify it. So that's what the parallel repetition theorem allows you to do very simply. I mentioned that it's quite tricky to prove, so the last part of my talk, I'm going to try to give you intuition for why it's so hard, and also, try to give you an aha moment of like maybe seeing some insight into how you actually do it. So we're going to go through a toy example. Let's talk about twofold parallel repetition, which is what I've been talking about most of the time for this talk anyways. So here's our goal. We are given a challenger, and we're promised that it has soundness S. So remember what that means. Like if you give me any adversary, the probability that they win the game against a challenger is at most S. Okay? Now, I'm going to take 2 copies of that challenger, and I would like to prove that this new guy has soundness S squared. But instead of doing that, I'm going to go by contradiction. So I'm going to assume that there is some super adversary. Here he is. Dun, da, 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 and he can win the twofold game with very high probability, like unimaginably high for us, because we would hope that it's S squared probability. And our goal is to design a single adversary, an adversary you can play against a single challenger and wins with probability much greater than S. If we can do this, if we can design this reduction, then by contradiction, this super adversary can't exist. Okay, so that's what we're given. We are starting with a twofold adversary. We want to end up at a one-fold adversary. And the first thing we do, and I recommend this, is just type check it. So the twofold adversary, he plays against 2 challengers. We want to play against 1 challenger. Our real adversary is going to play against 1 challenger. So our adversary, the one-fold adversary, will have to simulate one of the challengers, right? So he's going to kind of put up a fake challenger next to the real challenger and have the super adversary play against those 2. But there's 2 of them, and they might not be symmetric, right? The super adversary might do one of them first, or he might do something that entangles the 2 in some way. So should our adversary simulate the first challenger or the second challenger? I'll highlight in our heads, the super adversary is doing something that shouldn't really treat the challengers differently. But we're designing a proof, so we have to be careful and think of the 2 challengers as maybe different. I'll refer to challenger 1 sometimes as the first challenger, and challenger 2 as the second challenger. I hope that's clear. So to get intuition for how we're going to design our one-fold adversary, let's just look at Bayes' rule. So I've written it here. So you see the probability that our super adversary wins against both challengers. Well, that's just equal to the probability that it wins the second challenger, conditioned on winning the first one, and times the probability that it wins against the first challenger. I'll pause for a second so you guys can look at this because, yeah, Bayes' rule, it's quite tricky. So by assumption, we know that this number, this product, is bigger than s squared. So one of these two guys is definitely bigger than s. If they're both smaller than s, then, well, how could it be bigger than s squared? So let's assume that it's the second guy first. I have written in green. And if that's the case, then our job is really easy. We simply have the adversary, our one-fold adversary, simulate the second challenger, and then the super adversary knocks both of them down, and with very high probability, he's gonna he's gonna win against the first challenger. So our adversary just has to put up a fake challenger to make the super adversary actually able to play the game and do nothing else. So that's the easy case. The hard case is when that second term is small. So we can't simply have our one-fold adversary play the second challenger. We need to do something more, so we'll just rearrange the terms by assumption that this guy is smaller than s, so we get that this term is much bigger than s. But you see, this implies a natural strategy, which is that our adversary, our one-fold adversary, will try to simulate challenger 1 and have the real adversary, a real challenger, play as challenger 2. And the only thing we have to do is condition on the first challenger accepting. If we could guarantee that that first challenger always accepted, then by this equation, we would actually be done. Our super adversary would win against the second challenger with very high probability. So how can we make that happen? And now I'll take an aside. So the way I want to frame this is, you should think of this as like post-selecting on some event, this event that the first challenger accepts. So now instead of doing parallel repetition, we can focus on this task of doing some kind of post-selection. And now I'm going to take an aside to a classical problem. So let's say that the challengers, both of them, are classical. They're like flipping some coins, and they're generating some challenges, and they're sending them to us. How can we do post-selection now? Well, there's not too much, in the high level, there's not too much going on, right? We can simply try the two-fold simulation, and we can check if the first challenger accepts. And if it does, then we just forward the second response to the real challenger. And we know that because we saw in our simulation that the first challenger accepted, the second one also accepted with pretty high probability. And if the first challenger in our simulation doesn't accept, well, we just throw it away, we restart it, and we try to get to a time when the first challenger does accept. Okay, this is called rejection sampling. And the real proof is not as simple as I'm making it sound, but at a high level, this is the algorithm that ends up working. The first thing you would try, at least I would have tried it, is just like, can we just do rejection sampling quantumly? And we're at a quantum conference, so many of you probably know that the answer is no. We get a challenge from the real challenger. Remember, he's the second challenger. But when we run the protocol once through, we're going to end up having to check if the first challenger accepted or not. And that act of checking the first challenger is going to mess us up. It's going to destroy our state in a way that's like kind of unrecoverable, or at least we don't know what's going to happen afterwards a priori. So we can't simply just try again and again and again. That doesn't work. We can't do that. So we're going to have to get a little bit fancier. Oh, my clicker is slow. Okay. I'm going to reframe the problem and bring in a little math, just to, like, not too much, but just enough to understand what we need to do. And I'm going to remind you, the high-level strategy is that our adversary is simulating the first challenger, and there's another challenger, which is the real challenger. Our adversary that we're designing is playing the one-fold game. So it's like playing against one real challenger, but it needs to simulate the first challenger for the purposes of getting the super adversary to work. Okay. I'll just write down a state psi. I don't know what it is, but let me just let the state psi be the state of the entire system after the super adversary gets the challenges from both challengers. Remember, our one-fold adversary is simulating the first challenger. So this it's like you can imagine that in the mind of our one-fold challenger, it has A and C1. So A is this adversary's private register, C1 is the first challenger's private register, C2 is the second challenger's private register, and the first challenger is inside of our one-fold adversary. Second challenger is out there challenging us, unfortunately, so we can't touch that. Yeah. The second thing I'm going to define is this projector, pi tilde. And I'm not going to tell you what it is formally, but you should think of it as a projection onto what we want. Remember, we want to post-select on the event that the first challenger accepts. So this is like some projector, and it only has to touch the adversary's private register and the first challenger's private register, because it only depends on the first challenger. It's just the event that the first challenger accepts. And what does it mean to do this post-selection? Well, it just means finding this projection. We want to take our initial state, psi, my clicker, and just take it down into the subspace of pi tilde. And if we could do that, then the probability that the second challenger accepted on this state would be pretty high by the Bayes rule thing. So we're up there, and we want to get down here. And I put like the normalization here because the goal is to get a normalized copy of this state. So now that we've like phrased this problem like this, let's think about how we could do this. A lot of you might know this amplitude amplification algorithm, which basically does something like you take a state psi and a projector and you like kind of do some flips around them. You apply some signs. And you end up starting at psi and ending in the projector. And so you might think, well, that's exactly what I'm trying to do. I'm starting at psi, and I'm ending in pi tilde. But remember, like I've forgotten it too. But anyways, in the real protocol, like I've been highlighting, we don't have access to C2. And psi is some crazy entangled state across all the registers. So we can't actually do this projector, this unitary. Now, we can't get psi, that's why I said we don't have C2, but maybe we can get another projector pi that contains psi, right? We know roughly the area that psi lives in, and where does it live? It lives in the space of valid challenges, right? So there's some subspace which you could define, which is like anything that could have been a challenge from the first challenger. And you definitely know that psi is one of these guys because it came from the first challenger. So now I have these two projectors, pi, which is where I currently live. I live somewhere in pi. Psi lives somewhere in pi. And pi tilde, which is where I want to end up. I would like to end up projecting onto pi tilde. And for those of you who are more into crypto, you might be aware of a lot of recent progress in the past, I guess, 2 years on this alternating projector stuff. And basically the summary of that work for the purposes of this talk is that if I simply alternate pi and pi tilde, eventually I will map any state in pi into pi tilde. And this seems like great, like it seems like the killer app, like we've done it. But these algorithms don't actually give you any promise on where you end up in pi tilde. And to be a little bit more precise, they only actually implement this projection for what are called singular vectors of the product. And it doesn't suffice for us to just get any vector in pi tilde. We really want to take wherever we started and end up in the projection because we started at some specific point in the protocol. We didn't start anywhere. We just don't know where we started, but we know that it's an important place where we started, and we know that where we end up is also important. So it doesn't suffice to just get some random vector in pi tilde. We need the projection. So to wrap things up, I'll tell you like what you actually do. So let me just write psi in the eigenbasis of pi. Remember, I know that psi is a vector in pi, so I can write it like this. And I'm going to write the projection onto pi tilde. Very simply, it's just like I have the same coefficients, and I have these inner products with the w's. Here the w's are a basis for pi tilde. And ideally, what I get is like times the normalization constant. I just get like this state times the normalization constant. And let me now write down the product of those two projectors and its singular value decomposition. So here, the vi's are a basis for pi, and the wi's are some basis for pi tilde, and the ci's are the inner product between vi and wi. So you see, this is kind of like encapsulating the operation you want to do. We want to map a VI into WI times CI. And I've written it out here, like here the VIs are in our projector pi. And these guys are exactly the things we want. So how can we do this operation? The short answer is we look towards recent developments in algorithms. So the QSVT is something that allows us to essentially perform a unitary that acts like that projector with some with some polynomial post-selection factor. And by doing this, essentially we get like a free amplitude amplification that is like oblivious. We get to do this approximate projection. And I've omitted a lot of details, but that's essentially the main technical idea of the paper. I'll leave you with open questions, and you can take a look while the questions are going on. But thanks so much for listening to my talk.
Thank you very much. For questions, I would invite the audience member to queue at the microphones. And while that's happening, please feel free. Let me just ask a question about the, your definition has computationally polynomial time, was it an adversary? Mm-hmm. So what's the significance of that? Because we could have statistical properties of the commitments.
Oh yeah, well, you're right that you could have statistical properties of commitments, but it's known that you can't have everything you want for free. Like something has to be computationally secure. I don't know who proved this, but it's an old result. And more generally, in the bit commitment case, this is why you need to talk about computational security. Like you can't have only statistical security, but also in general, a lot of things you might like to do in the real world are interactions between efficient parties. I mean, I don't know any unbounded gods personally. So, everything I would be doing would be between two efficient parties, and I would like to understand those a lot. So, yeah.
Does the result hold for unbounded parties?
There's been a lot of work on parallel repetition for unbounded adversaries. So, yeah, there is like a separate parallel repetition theorem for interactive proofs, which are when the adversary is unbounded. Yeah.
Any more questions?
Thank you again.
Okay, if not, let's thank John again.